Well, welcome everyone here to Drobo. It's a pleasure to see all of you here. As Tom said, we're going to take you through our latest innovative technology here at Drobo, which is really how we implement SSD support and automated tiering inside of a Drobo. So very similar. If you know about Drobo's BeyondRAID technology and how we automated data protection in Drobo, it's the same design premise for how we're automating tiering inside of a Drobo. For those of you who do not know some of the details about how a Drobo has worked, we are going to be going through a little bit of a primer on Drobo's BeyondRAID technology. So on our storage stack, and Rod's going to take you into some details there. One of the keys is how that technology is very, very key to how we implemented data tiering. So they're very complementary technologies in making this fully automated. So we have about 45 minutes. So as I go through this, feel free to, we're going to keep it moving, but feel free to ask questions as we go along the way. And we'll also leave some time at the end for additional Q&A, but we'd love to have this be interactive. One of the fundamental differences of how a Drobo works versus a traditional RAID array is a Drobo, or a single physical Drobo, is a single pool of storage. So in a Drobo, there's no concept of dispooling or creating a RAID group. The end user inserts drives, and they could be of mixed capacity, they could be of mixed spindle speeds. They insert drives, and the Drobo recognizes those drives, pulls those into an aggregate pool of storage, and presents that as usable storage to the user. The only thing the user has to do is select. There's one checkbox. It's your data protection policy. Do you want to protect from a single drive failure or two simultaneous drive failures in a Drobo? And that's it. There is no unprotected mode inside of a Drobo. So off the bat, just the introduction of drives into a Drobo and pooling them is very simple. Now, how we make all that work is really where the secret sauce comes in, and it has to do with what we call zones, or have appear as BeyondRAID zones. So where a traditional RAID array inside of a single RAID group would have, it'd be one mirror or one stripe with parity or one stripe with double parity. Inside of a Drobo, there's thousands of little zones. If you look at a zone individually, it'll look just like a RAID group. But inside of a Drobo, there's a lot of them, and Rod's going to take you through initially how we create zones and how that part of the storage stack works.
Okay, so a zone really is the fundamental unit of redundancy in a Drobo. And as Eric said, we have thousands and thousands of zones in the system. A zone is roughly a gigabyte. It's actually 1,023.75 megabytes, but roughly a gigabyte. And so if this is our array, we've got some small disks over here, some medium-sized disks, and some big disks. We can create a zone over any number of those disks. So we could create one big fat stripe like this, and that would be a big wide parity stripe. We could create on these disks slightly thinner parity stripe. So now we've been able to take advantage of this little bit of capacity here that traditional RAID just can't do that. And then we can create over this side here another little thin parity stripe, and this is the really cool part. In this over here, if we wanted to, we could create, if these were dual redundant zones, you'd have a parity and a second parity piece. In this little stripe here, instead of a stripe, we could actually make that a triple mirror. And so if we wanted to, instead of taking this really big fat stripe here, we could make this, and let me just we could make this a triple mirror, or we could make it a little RAID 0 here, and a RAID 0 here, and a RAID 0 here, and then we could mirror those all together. So we still have our redundancy. But we can basically slice and dice the big blob of storage that is the storage pool any way we want using a zone. And like I said, fundamentally that is what a Drobo is a big collection of zones. Big system will have maybe 30,000 zones. Little system like the small 4-bay stuff we were talking about earlier can have 16,000 if it's a 16 terabyte system or whatever fits in there. And that actually brings us on to zone rebuilds. So because these zones can be any shape we need to make them, at any time we need to make them, if this piece failed, well, in a normal traditional RAID, you now have to replace that piece and rebuild the entire array. But what we can do is we can say, well, that's okay, we'll just create a zone like this and extend it over here using those disks, and then rebuild. So we can immediately start to rebuild, and if there's enough capacity spare after that piece has failed, we can rebuild the entire array back to redundancy without any intervention. And it will just do that automatically.
So Rod, so you're saying the zones that were not affected by that drive do not have to be rebuilt. They can stay
Absolutely.
the same.
That's a good point. Because we know where the data is, we only end up rebuilding the zones that actually have been degraded by the failed piece. So this little mirror, triple mirror I drew over here is not affected by this failed piece. We don't have to rebuild that data. So if one of the small pieces, if we had a really small piece over here, somewhere that failed, then any zones in basically this big blob of storage here wouldn't have to get rebuilt.
So if you had a bunch of small drives and you had like one 2 terabyte drive, if you kept pulling all the small drives out, eventually all your data would be sitting on the computer.
It would. And in fact, then we do actually go down to self-mirroring at that point, because we want to keep 2 copies of data if possible. That still protects you against single block errors. Obviously, you don't have redundancy against a piece failing if you've only got one piece left, but we will actually then end up, as you said, slowly migrating all the data into that one final piece that's left.
Actually, I'm curious, before he goes on, how many of the delegates actually have a Drobo already?
Only 2.
Wow, I'm surprised.
You should fix that.
Yeah,
That's an opportunity.
I'm sure nobody would object to that, Jim.
Stephen, you should ask the question, how many of the delegates have got more than one Drobo?
Yeah. How many delegates have more than one Drobo?
It's the same one. Same one.
How many
bigger
delegates have got more than 2 Drobo?
No, I only have 2.
Little one-upsmanship.
And so that's fundamentally that's how our storage stack lays out data. It's a very granular and very efficient way of laying out and managing data. It's also very flexible, as Rod says. As a drive enters the array, the technology can spawn new zones. It can migrate data from one zone to the other, so it can rebalance the array and optimize it over time. As a drive leaves the array, it does the same thing. It can move data from one zone to the other, eliminate a zone, to maximize whatever capacity you throw at the Drobo. And one of the ways that the array is able to do that is aware of data, is aware of where data is and where data is not. We're not going to go too much into our thin provisioning and thin reclamation technology in this presentation, but every volume on a Drobo or every LUN on a Drobo does pull from a common pool of storage. So typical with thin provisioning, but it also returns data right back to that common pool inside of the volume. So if the user creates user data inside of a formatted volume like an NTFS volume, it will pull from that common pool. If data is deleted inside the NTFS volume, it will also return the data back to that common pool. That data-aware technology is also very critical for how we do tiering. But instead of just making decisions that we have been in the past only on utilizing or maximizing capacity in the array, there's also decisions now being made to maximize performance in the array. So Rod, if you want to continue on logical tiering and continue around data aware and how we do tiering at a logical layer. So this technology not only optimizes, Rod's going to go into how it not only optimizes if you have a faster tier of storage through the use of solid state drives, but also if you're using only spinning media or only the same speed of storage across all your drives.
So that's actually an interesting question. Why do logical tiering? Why have a tier if I've only got 12 hard disks? Essentially only got 1 tier of storage. Why do tier? Well, actually, it's because the flexibility that the BeyondRAID zone gives us means that we can actually create 2 distinct performance profiles inside that one big pool of hard disks. Even though it's only one pool of hard disks, there's no physical difference in the disks. There is a performance difference in how you lay the data out. And the fundamental reason we want to do tiering is because if I have a big parity stripe, And I've got if it's a dual redundant parity stripe, everything we do with Drobo is dual redundant by default. If I want to write a single 4K block into this piece of the array here, what I have to do is read the entire stripe, update this block to recompute the two parities. And that's obviously time-consuming and expensive. But if I can lay out this zone, instead of a big parity stripe, I can lay it out as just a triple mirror. And now if I want to update just this one block here, well, I write that one block, and I write its mirror here, and its mirror there, and we're done. And clearly that's a lot more efficient than having to mess around with this big fat parity stripe. And likewise, if we were with 12 disks, it would be more performant to actually use four-piece RAID zeros. Even though these are stripes, there's no parity here. So we still have the same performance benefit. But now we can stripe the data across. If I want to write this block of data here, then I write, whereas in the stripe, the parity stripe, I'd have to go and read everything, recompute the parities. Here I can just write this block with the new data. I write the same block over here. I write the same block in the third piece of the RAID 0, and we're done. So we just mirror these three RAID zeros together to get a redundancy. But within each of those RAID zeros, there's no parity update to do, so there's no extra performance cost for writing that small piece of data. And of course, we don't have the density of IOs going to one spindle that you would have in an ordinary mirror. So we still have a lot of performance because we've got the stripe, but there's no parity to mess around with. So we don't have to do this big read, modify, write operation.
But you do pay a bigger capacity penalty.
You do lose capacity, right? So in logical tiering, and that's a very good question. The logical tiering, it wasn't a question, a very good statement. The logical tiering is there's no real disadvantage to reading this block in a RAID 5, RAID 6 type parity stripe versus reading this block in a mirror stripe that we call them, which is similar to a RAID 0+1. And there's no disadvantage in reading it from a simple mirror. So in logical tiering, we only actually allocate a small piece of your storage pool, essentially as a write buffer. So we can sync writes into this at high performance, but there's no advantage in keeping them there. So as that fills up, we can roll those off into the fat parity stripes that we can use then to maximize your storage capacity. And that essentially is.
So is it actually a three-way mirror in a
You
1200i?
Drobo lets you choose between single or dual redundancy. So if you chose,
Oh, so if I select dual redundancy, it's a three-way mirror
Be a
that
three-way mirror.
destages to a RAID 6.
Yes.
Like, okay.
yeah, it is almost a RAID 6. It's not quite, but it's
Yeah.
still dual redundant and parity and Q single. You want to think that?
Sure. So with that, like as Rob was saying, and it's a relatively small amount of space dedicated to this logical tier, if you have all hard disk drives, but usually the payload with random transactional IOs is very small. So what you're doing is you're accelerating a lot of the small IOs, random IOs that are sometimes blocking the larger IOs or the stream that would be going to the to the peak plus Q stripe or the single parity stripe.
So does that also act as a log structure to extend the size of the D stage so that we're writing full RAID stripes?
That's a good question with a complicated answer, but essentially yes.
It was a relatively complicated question.
It was. when we do the migration from the mirror stripe into the RAID 5, the parity stripe, we will actually end up only writing whole stripes at a time. In fact, we translate the whole zone. So if you remember back when we talked about zones, they were a gigabyte each,
Right.
roughly. So we would take the whole gigabyte. And for us, a zone is always a gigabyte. So a mirror stripe zone contains a gigabyte of user data. The parity stripe zone is also a gigabyte of user data. So there's the same amount of data, and we can optimize to write that internally in whole stripe lengths.
Oh, so you destage a gigabyte at a time?
Yeah.
Okay, so there's multiple mirror zones.
Yeah,
so
so,
that,
in the,
so that I can be filling one as I'm emptying the other.
absolutely, absolutely. And so the limit there is a soft limit. We can adjust it as we need to.
So does the customer actually define the number of trip stripes, or is it all internal? Or?
All of this is fully automated, which is why we're doing this. The user does not have the ability to carve out a pool of storage and say, I want this to be, RAID 10
Triple
for my
RAID,
high
triple
performance
mirrors,
volumes, and I want to use the rest of the storage as a RAID 6 group for my bulk storage. All of this is under the hood to the user. All the user says is how many simultaneous drive failures they want to prevent against, and then you just carve up volumes and assign them to servers.
And so you automatically create these triple mirrors for a write buffer and the other zones, parity stripes for the read activity and for the ultimate destaging of the write data.
Correct. So the user, from a user perspective, they do not know any of this is going on. We're implementing the technology into the hood, so what they experience is more accelerated storage than if we weren't doing it, and while keeping the capacity utilization high. This is a very small amount of allocated or carved off space to do that, and while giving them the level of protection that they have set from their upfront policy.
Similar to-
Right.
But it's important to notice that because we are data aware, we actually only write I/O into the mirror stripes or whatever we're using for the logical tier that would benefit from that layer. So if you're copying bulk data, if you're streaming data onto the array, we can write that directly to the parity stripes because we can coalesce that into whole stripe lines, and there's no penalty for doing that. If you overwrite a whole stripe, if in this example here, if I'm actually writing a block in each one of these pieces of the stripe, there's no penalty. You can just overwrite the whole thing because I can compute the two parities directly in memory. You don't have to read the old data, completely erasing it. So what goes into the logical tier is only data that we decide on the fly. We decide will benefit from being written into that tier from a performance perspective. And so typically that's transactional data. Small random writes.
It's not actually, you're not using a log structured file system for the stripes.
No.
So before we move on, one thing I do want to know, does anyone have, I know we have a Drobo here. You have a face, oh, you have one. I love how my boss is my personal
carry it
Dana
around
White. So
Usually in my pocket.
the only real user actions with the Drobo that a user has is pretty much inserting the types of drivers they want, carving up the available storage capacity and assigning it to servers, so creating volumes or creating LUNs and assigning them to server, and essentially then maintaining the Drobo. And a Drobo is maintained almost solely by the lights on the front of a Drobo. So on a Drobo, like this is our faceplate, and the lights shine through it. Every drive has a status light. It's green, yellow, red. The indicators are actually on the back of the faceplate to make it as easy as possible. And there's a capacity gauge on the front that gives you a visual indicator of how much usable capacity you have left. And the capacity gauge is accurate across all your volumes. So because we know where data is and where data is not, we're able to present to the user a very accurate capacity gauge. So for example, if the capacity gauge goes up and we get to, let's say, around 80%, and there's an empty drive bay in the Drobo, we'll actually light up the empty bay with a yellow light saying, you may want to add a drive here so you're running low on capacity. If we're really running low on capacity and the thing's getting closer to like 95% and above, that light will be red. Even though we're a thinly provisioned array, we actually have processes that run that prevent the user from ever running over the cliff. We do not allow the host to essentially affect or damage its file system by running over the cliff. We will incrementally start to essentially slow down the acceptance of writes before it ever reaches 100%. So the user doesn't have to know about where exactly they are with each volume, and do I have to set a quota and set up email alerts if I get there. You'll get an alert that you're running 80% low on capacity, but a lot of the details associated with managing a thinly provisioned volume isn't in a Drobo. So that's really all the user has.
So you're slowing down writes as it fills, but what happens when it does get there?
Bad things.
For example, what happens to me when I ran file vault 2 on my Drobo to see what would happen?
Well, there's certain things with the, I mean, we understand what's going on inside the file systems.
Yeah.
There's certain things in a file system that could potentially confuse a Drobo. But the way that the technology is implemented is that you'll never get that 100% sector written, or I should say LBA written in that available volume. So it'll slow down until it gets to that point. Ron, do you have any other details on that?
And say what's going on here and not complete.
Yeah, I mean, eventually you're right. Eventually, a copy won't complete, and the unit will be in a essentially the same to the user. Will be the same effect as a read-only type mode.
So you can get it to that point quite easily.
Yeah.
You just have to create a sparse file that doesn't actually have any content. And because you're reading the MFT on the NTFS volume, you can fool it into thinking that the volume's actually got real data on and overload it. Because I've done that before on mine as a test. Which is quite...
Yes, we've done stupid things to your product. You just have to know
great.
this.
It's our job.
That's right. So, Tom, did you want to? You had an arrow here. Did you want to?
We'll just take a 30-second break, maybe.
That's part one.
Right. Yeah. That's kind of the first half before we go into some of the details of continuing on of tiering from logical tiering and how we introduce SSDs into a Drobo and things like that. So, is there any questions, or does anyone need a quick break?
I've just got one question I would like
Sure.
to ask if I can. I still don't understand why you haven't introduced the ability to proactively remove a disk rather than have to go into a rebuild scenario when you want to take a disk out.
Hallelujah. Somebody's been asking for a while.
No, it came out last Tech Field Day too.
Yes, it did.
It did come out last Tech Field Day.
Repeat the question again?
He
So
wants to be able to
I
eject
want
a
to be able
drive.
to, I want to proactively decide I want to take a disk out. So that rather than have to pull it out and then it goes into rebuild mode, I can say I'm taking that disk out.
Don't go into rebuild mode.
No, go into rebuild mode and then
but
tell us when
Proactively,
you're done.
proactively go into
Yeah.
rebuild
and then
mode.
I'll pull it.
Go into rebuild mode while it's still protected.
Yes.
Because right now, if you've only got one single drive protection and you pull out your drive, you have no protection
Yeah.
while rebuild is happening. And rebuild can take quite a while on consumer SATA drives.
Yeah. So it gives you that degree of control whilst you're waiting for the data to be spread everywhere else, that if something did go wrong during that process, you didn't lose data.
Yeah, and then once the drive is ready to be removed, flash the LED behind
Yeah.
it, below it, going, yep, you can pull this one out now.
No, that's a very good point. Especially when upgrading, as I'm sure that's why you're asking.
Exactly.
I want to be able to upgrade my drive that's already in place. So that's another thing that if you those that haven't used a Drobo, if the Drobo's completely full, you can pull out a small drive in the Drobo and introduce a larger drive to it to continue to expand capacity after all the drive beds have been completely populated. So yeah, that's a very good feature request.
You accept any sorts of SATA drives? I mean, so I could go out and buy any SATA drive I want, plug it into your carrier.
There's no carriers.
There's no carrier.
And they can even be mismatched drives in the same set.
I understand the mismatch, but anybody's drives can fit in.
Any 3.5-inch SATA drive will fit into any Drobo. The new B1200i array, which we have over there, will accept any 3.5-inch SATA or SAS drive.
So 4 terabyte is supported today?
Correct. Supported today.
4K is supported.
Yes, 4K.
I was saying 4 terabyte.
Yeah,
but
so-
4K sectors too.
Yes,
I
absolutely.
don't think you can get a 4 terabyte without them, can you?
Probably not.
Seagate makes them.
Without
And we also won't optimize for the 4K sector drives. You don't have to mess
That's
with the
what
jumper.
Yeah.
You just plug them in and take care of it.